Resolving of vectors into component vectors can be resolved into horizontal and vertical components as shown below. Resolving a force F in figure 120 resolution of vector, we see that the force F at an angle theta. The vertical axis is force sine theta, while the horizontal axis is force cos theta. Then figure 1.21 example shows a resolution of three vectors in the same Cartesian coordinates f1 and f2. f1 is acting on a theta, on an angle theta, while f2 is acting on angle phi. F sine theta is for the one on the left side, while f cos theta is for the coordinates on the right side. Resolution of force of above figure 121. Resolve the force above force acting on the body into its components. The forces F2, F1 makes angle theta and phi respectively with the horizontal. Hint: if the body in figure 121 is in equilibrium, horizontal component of F2 is equal to F2 cos phi. Horizontal component of F1 is equal to F1 cos theta. Total horizontal component Fx is equal to F2 cos phi minus F1 cos theta. Vertical component of F2 is equal to F2 sin theta. Vertical component of F1 is F1 sin theta. Total vertical component Fy is equal to F2 sin phi plus F1 sin theta minus F3. Example 3. Find the tension in both strings represented below. The strings are carrying 20 Newton body, and the tension in T2 is at an angle of 30 degrees to the horizontal, while the tension of the string of T1 is 45 degrees to the horizontal. The horizontal component of the string T2 is T2 cos that, while the horizontal component of T1 is T1 cos 45. Solution: resolving the T2 and the T1 into horizontal and vertical components above, you have the sum of Fx is equal to 0 and sum of Fy is equal to 0. T2 cos 30 is equal to T1 cos 45. This will be our equation 1. T2 sin 30 plus T1 sin 45 is equal to 20. This will now be our equation 2. Solving equations 1 and 2 will give T2 is equal to, in bracket, T1 cos 45 all over cos 30 is equal to, in bracket, T1 times 1 over square root of 2 all over, open bracket, square of 3 over 2, close bracket. T2 is now equal to T1 times 2 all over, in bracket, square root of 2 times square root of 3, which will now give us equal to, in bracket, 2 over square root of 6 times T1. Substituting in equation 2, then we have that, in bracket, T2 over square root of 6 close bracket T2 times half plus T1 half 1 over square root of 2 is equal to 20. 0.408 T1 plus 707T1 is now equals to 20. 1.115T1 is equals to 20. Therefore, T1 is now equal to 20 over 1.115, which gives us 17.94 Newton. So T2 will now be equal to 2 over square root of 2 times 17.94, which will give us 14.6 Newton. Resultant velocity using vector representation. If a boy is running along the deck of a ship in a direction OA and the ship is moving in a direction OB, the boy will move relatively t the c along a direction OC between OA and OB. Figure 1.23. Now in 1 second, the boat moves from O to B, where OB represents the velocity of the boy in magnitude and direction. Thus, in 1 second, the net effect relative to the C is that the boy moves from O to C. It can now be seen that if the lines OB are drawn to represent in magnitude and direction the respective velocity of the body and the boy and the ship, the magnitude and direction of resultant velocity of the boy is represented by the diagonal OC of the completed parallelogram having OA, OB as two of each size. OACB is known as parallelogram of velocities. Conversely, a velocity represented completely by OC can be regarded as having an effective part or component represented by OA and other components represented by OB. Figure 123 resultant velocity. A force X is being drawn at an angle of 30 degrees. ABO represents the relative velocity. Example 4. A swimmer whose velocity in still water is 4 km per hour set out a straight angle to the bank of a river which is flowing at 3 km per hour. Draw a sketch of his path showing the water. Calculate his actual velocity through the water. Solution. Since the man is moving in 4 km per hour, then he now moves from O to A. Then, meanwhile, the river is flowing with a velocity of 3 km per hour, moving from A to B. Then the resultant of the movement of the man is OB. But according to the law of vector resolution, forces start where the force ends. So, since the man is moving in the direction of AB, AO, the AO will now represent the movement of the vector or the direction of the man, followed by AB, which is the direction of the stream, which is moving at 3 km per hour. Then OB will now represent the resultant of the movement of the vector. Since OAB is right angle triangle, the actual velocity through the water is given by OB equal to square root of square of OA square plus AB square, which is equal to square root of 4 squared plus 3 squared, which is equal to